Have you ever felt that sinking feeling in your chest? It is that specific, cold, Monday morning heartbreak that only an analytical chemist truly understands. Imagine this. You've worked for weeks preparing 200 precious samples. You've optimized the extraction, double-checked your mobile phases, and on Friday afternoon, you hit start on a 72-hour marathon analytical run. You walk out the door dreaming of a weekend of rest and a Monday full of beautiful data. But when you walk in today and open that sequence, you see it. Around sample number 10, the instrument started to drift. Whatever the cause, a dirty source or a failing column, the result is the same: 190 samples of absolute garbage. All that solvent, all that instrument time, and most tragically, those irreplaceable samples are wasted. The trap is treating the mass spectrometer like a set-and-forget machine. In operational excellence, we treat it like a living organism. If you aren't checking its pulse, you aren't doing science, you're just hoping for the best. Today, we build your early warning system. Before we get into the technical settings, we must address the philosophical shift required for management. In high-stakes consulting, we move beyond the set-and-forget mentality and treat the mass spec as a high-performance athlete. Just like an athlete, its performance can degrade due to stress, fatigue, or contamination. If you aren't monitoring the pulse of the system throughout the run, you are flying blind. Today, we master the sentinels of data, the specific quality control strategies that allow you to catch drift before it ruins your week. By implementing robust QC, you move from being a victim of the instrument's whims to being a master of its operational health. By the end of this module, you will sleep peacefully while your instrument runs, knowing that if something goes wrong, your system will tell you. Before we dive into the math, let's clear up a major piece of confusion. People often use QA and QC interchangeably, but as a strategist, you must know the difference. Quality assurance, or QA, is your broad, high-level plan. It is the strategic blueprint that maintains quality across the entire program, the why behind our work. Think of QA as the architectural blueprint for a safe bridge. Quality control, or QC, is the tactical execution. It refers to the routine technical activities, the how, of day-to-day error control. If QA is the blueprint, QC is the inspector who walks the bridge every single morning to make sure no bolts have come loose. Without a QA plan, your QC has no purpose. Without QC tasks, your QA plan is just a piece of paper. So how many health checks do you actually need? Many labs cut corners to save time, but in high-stakes environments, the pro tip is to never be afraid to run QCs. According to professional standards, the total number of QCs must be greater than or equal to 5% of the total unknown samples. However, there is a floor. You need a minimum of 6 QC samples, or N equals 6, per analytical run. This is because we require 3 concentration tiers: low, mid, and high, run in duplicate. But here is the critical strategy. You must use strategic bracketing. By placing your QCs at the start, the middle, and the end of your sequence, you can identify exactly where a drift began. If the QCs at the end fail, you might save the samples from the first half of the run, instead of losing the entire batch. Once you have your QC data, how do you decide if the run was a success? We use the 15% standard, which we call the boundary of truth. For an analytical run to be considered valid, at least 67% of the total QC samples must pass. Passing means the measured value is within the tolerance threshold of plus or minus 15% of the true concentration. But it's not just about the total. You also have tier requirements. At each concentration level, low, mid, and high, greater than or equal to 50% of those specific samples must pass. If your high QCs miss the mark by 20%, it doesn't matter how perfect your low levels were. That level has failed, and your data is now suspect. In regulatory science, there is no close enough. The 15% bias rule is strict and unforgiving. While batch QCs are vital, you also need to know if the current injection is healthy. This is the role of internal standards acting as real-time sensors. Think of the internal standard, or IS, as a check engine light. We add isotopically labeled compounds to every single sample to act as health sensors for every injection. Because the IS and the analyte are in the same environment, a dropping signal indicates diagnostic drift, the result of instrument fatigue or source contamination. We set a strict action threshold. If the IS signal drops by more than 50%, you must stop the run immediately. A wise architect listens to the sensors of the instrument before the heartbreak of a total failure happens. Finally, we have the ultimate test of reliability, incurred sample reanalysis, or ISR. Even if your artificial QCs look perfect, we must prove the method handles biological complexity, because real blood is not spiked plasma. The strategy is simple. You perform a 10% reanalysis for the first 1,000 samples and 5% thereafter. We focus these repeats on the Cmax and elimination phases to prove the method works across the entire concentration range. The criteria are slightly wider because real-world matrices are complex. At least 67% of the repeats must be within plus or minus 20% of the mean. ISR is the final stamp of real-world reproducibility, ensuring your science holds up under the toughest scrutiny. We've completed our operational excellence blueprint. You now have the tools to catch drift before it catches you. Remember, QA and QC define your strategy and execution. Use the 5% rule in bracketing to establish data protection. Use the 15% bias as your unwavering boundary of truth, and use the ISR test as your final stamp of reproducibility. Always remember the golden rule of the lab. An ounce of prevention is worth a gallon of solvent. By implementing these health checks, you are no longer a victim. You are a master of analytical integrity. In our next module, we will explore targeted versus discovery workflows. I'll see you there.